So let me prove this theorem that for every prime p and every natural number n, there is a finite field fp to the n, and there is only one up to isomorphism, like this. The existence we have seen already kind of in some cases, like if you take f2x mod x cubed plus x plus 1, that would be a field of order 8 and so on. But we'll actually construct this in one go, all of these fields, as splitting fields of a specific type of polynomial that's closely related to this Frobenius homomorphism. Can I recall that once more? It's too important. So if you have a field f of finite characteristic p, then p, remember, has to be a prime number. Then you take this function from f to f defined by x goes to x to the p. So it's raising to the pth power map. That actually happens to be a field homomorphism because of this formula a plus b to the p equals a to the p plus b to the p, which is available in characteristic p. Okay. So a plus b squared would be just a squared plus b squared. So a field homomorphism that is non-zero, it certainly takes 1 to 1, so it's non-zero, is necessarily injective. And if you are in a finite field, then it's actually also surjective. So if f is a finite field, then sigma from f to f is a 1-to-1 map, but on a finite set it has to be onto, so is a field isomorphism. It's called the Frobenius automorphism. So, having recalled that, let's start with the proof. So first we have to show that there is a field of order p to the n, and then we have to show that given any field of order p to the n, that any finite field first of all has order p to the n for some p and n, some prime p and some natural number n, and then any two of these are isomorphic. So let's prove this uniqueness part first. So let k be a finite field. And then it has a characteristic, finite characteristic. Let p be the characteristic of p, a characteristic of k. So this is a prime number. Then is a prime. Then if you take 1 of k, and then 1 plus 1, which I'll call 2, and then 1 plus 1 plus 1, 3, you'll go up to p minus 1, and then the next step you get back to 0. And the addition and multiplication of these elements of k is exactly the addition and multiplication of z mod p. So this forms a copy of z mod p, or what we call fp, inside k. So k is an extension of fp. And k itself is a finite set. So of course it's a finite dimensional extension. So it's what we call a finite extension, meaning it's a finite dimensional vector space over fp. So it has a dimension. Let n be that dimension. So k is an n-dimensional vector space over this field with p elements. So an element of k is a vector of length n, and each entry has p choices. So k has size p to the n. Let's call that q. So I'm going to write q equal to p to the n. So now let's look at the multiplicative group k star, meaning k minus 0 under multiplication. So the multiplicative group k star has order q minus 1, because k has size q, so it has 1 less. So if you take any element in there, so any non-zero element of my k, then its order is a factor of q minus 1. So a to the q minus 1 is going to be the identity of k star, which is called 1, right? So you get this equation that a to the q minus 1 is 1 for every non-zero element of the field. So allow me to multiply by a, and then I get a to the q is a for all a in k star. But this actually holds for a equal to 0 as well, so it actually holds for all a in k. But what does this say? This says all the q elements of k are solutions of the degree q equation polynomial. I think for polynomial we say roots, are roots of the degree q polynomial x to the q minus x. Saying that a to the q equal to a for all a in k, this means that all these a's are solutions of this equation, this equal to 0. So they are all roots of this polynomial. So all these elements of k equal to literally roots of this one polynomial. And the sizes are the same. The size of the field is q, the degree of this polynomial is q. And this is so tight that this makes everything work out very quickly. So in particular, you immediately see that k has to be the splitting field of this f. Or maybe we should even observe before that this polynomial in any case cannot have any repeated root in any extension. If you calculate its derivative, you get q times x to the q minus 1 minus 1. Just formally the derivative. But q is p to the n and p is 0 because we are in characteristic p. So this is minus 1, which is not 0. And it's a constant, so the GCD of f and f prime is just 1. So f cannot have repeated root in any extension of fp. By the way, maybe I should emphasize that I'm thinking of this guy as a polynomial with coefficients in fp. Okay, so this shows, so of course this polynomial splits in k, but it cannot split anywhere smaller, because if it splits anywhere smaller, it has q distinct roots there. But then m would have size at least q, but k already has size q, so it cannot split in anything strictly smaller. So k has to be, let's write it out. F splits in k and cannot split in anything smaller. Cannot split in a proper subfield. Because to split it, you at least need all the roots. There are q roots. And already k has all those, k only has those q roots. So you cannot throw anything out of k. So k equal to the splitting field of this equation over fp. And this is very unusual. I mean, usually when we write splitting fields, it's the field generated by the roots of a certain polynomial. So it has those roots, but it has plenty of other things. In this case, the field itself consists of all the roots. It has nothing else. All the elements are roots of this one single polynomial. Okay. So now that you know this, now the uniqueness part of the theorem follows from the uniqueness of splitting field. From uniqueness of splitting field. But it also tells you how to construct it. For the existence, I'm going to start with this polynomial in fpx. So take a prime p and a natural number n, right? And consider this polynomial and look at the splitting field over fp. Let f be a splitting field of this polynomial. And at the end of the day, this f will turn out to be the thing that we want. But we don't know that yet. We don't know how big this f is. So what I'm going to do is I'm just going to collect all the roots of this polynomial in f and call that fq. Let fq be the set of roots of fp of this polynomial, fx in capital F. Because this is a splitting field, it has q roots in there. And we already saw that f has no repeated root, since f cannot have repeated roots. That's this lemma. We check the derivative, right? We have that fq, which is the set of roots of this equation, has size q. But the claim is that fq is already a field. So note that fq is already a field. And this uses the Frobenius. So let A be in fq. Means what? Means that A and B are two elements of f, and they are both solutions of that equation. That means A to the q is A and B to the q is B. But then A plus B to the q is A to the q plus B to the q, because A plus B to the p is already A to the p plus B to the p, and q is a power of p. So you just repeat that a few times and you get this, which is A plus B. So that tells you if A and B are in f, so A plus B is also a solution of that equation. So A plus B is also in fq. And you can easily see that the product is also AB. So the product is also a solution. So the product is also in fq. Also verify for the negative n. Verify that A inverse is in fq and minus A is in fq. And this, you have to check the q equal to 2 case separately. But that shows fq is already a field, so it's a field of the right order. So we have constructed one. But by the way, in the end of the day, this now shows that this has to be f, because f was a splitting field, and this is potentially smaller, but my polynomial already splits here. Since f already splits in fq, it follows f equal to fq. So I could have actually said that let f be a splitting field of fx over fp, and f is a field of order q. But I didn't know that. Now I know at the end of the day. Okay. This is the existence. There's one more statement that is good to know about this, that this multiplicative group of any finite field is cyclic if k is a finite field. This theorem is proved in the notes. We won't have time to prove it now. So we'll go back to the general theory next.